the server type in this data center doesn't need, or it doesn't require any backup system, UPSs or generators. So like I said, we have overhead cooling coils. The coils have ECM motors that change the speed based on the pressure inside the hot aisle. So if there is no load from the servers, for example, then the fan on the coil will reduce the speed. The pressure still stay the same. And when we have higher load on the servers, the fans, the ECM fans, increase the speed and release the pressure from the hot aisle. You can see the temperature that we operate in between 110 Fahrenheit to 130 Fahrenheit in the hot aisle, and the supply air between 80 to 90. With the cooling tower, we don't need chillers in the Bay Area because, again, the white bulb temperature works fine, so we don't need the chillers over there. The electrical system, so we standardize all our electrical system. We're using 415 volt, 240 volt systems. All the servers get 240 volt PDUs with 43 kilowatt. All the electrical system are 100% rated. The PDUs, the busways, transformer, all the equipment. Our substation also, they reduce the voltage from 12 kilovolt to 415 volts, so we don't need another set of transformer and lose more efficiency or lose power. Like I said, the electrical distribution is, we're using 800M busways. Each busway is a 575 kilowatt. Because of the high density, and remember, those are 20-inch trucks, it's 10 times greater than the average industry. Those are custom-made busway, bus stops, PDUs to meet our demand, 43 kilowatt per rack. The PDUs, like I mentioned, 415, we had to use a high short circuit current PDUs, and because we bring in power right from the transformer, the short circuit is high, so we needed to use high-rated equipment with the short circuit. The transformer, like I said, 100%. The design is flexible. You know, busways, it's easy to maintain. If you need to replace the bus stops, just remove them, replace to a different type, size, no issues. There's a lot of flexibility with this data center, and then reliability is high. Again, we don't have a lot of equipment. We don't have crack units. We don't have chimneys, no RMF, flooded air over there. And just to give you some idea, the 5 megawatt data center, we took 3 other data centers in Intel, which they required 43,000 square foot, and we were able to take those 3 and put them in one data center, 5,000 square foot. So you can see the density, it's 1,000 watt per square foot, really high. Same for the other one. We have 3 other data centers, total of 31, about 30 megawatt, which takes 334,000 square foot, and we were able to squeeze them into one 30,000 square foot area. So what we learned from this process, where we started 5 years ago, how to improve efficiency, we used many things. The air segregation, you know, to improve efficiency. We know that the air segregation is important. You need to make sure you have segregation between hot and cold aisle, no leaks, or reduce the leaks as much as you can. Chimney cabinets also could work. And also, like I said, no raised metal floor. From the air management, flooded supply air design, we use variable frequency drive or ECM motors to change the speed with just a Modbus signal. The cooling management, you saw the 2, the wet side economizer also could be another one, the outside air and the closed couple cooling. We also raise the temperature. Again, no need, like we said, we proved that we don't need to reduce the temperature to 70. This is important, and we're showing with Intel that the servers that works with Intel, the Xeon and the latest CPUs can work with a high temperature without any issues. We went to a 415, 240. One important thing that we did with feeding the servers, we have 3 phases. We show the utility power from the company shows that most of the subs are happening in one phase, and the other 2 still remain balanced or stable. So if you feed the server between those 3 feeders, ABC, I mean phase A, phase B, and phase C, even if one fails, the other might keep the servers running. And actually, again, like after 3 years or 5 years, we don't have any much issues with the power disturbances. High efficiency transformers, and in some cases, not in those 2 data centers where we need A and B feeder, UPS, and another feeder, we use the other as utility because the UPS is really reliable. So if something happened to utility, the UPS keeps the server running. We also use, like I said, 1100 watt per square foot, a multi-tier room design instead of splitting between many data centers, and this densification which maximize power and space and cooling. Okay, so that's it for me. Like I said, you can find all the information, all the white papers for those data centers at itandintel.com. Thank you very much.
Hi, my name is Brandon Hong. I'm the electrical systems engineer at Lawrence Livermore Lab, and we're located over in Northern California on a square-mile campus. With our Livermore Computing, we have a few facilities that total about 100,000 square feet of computing space and over 50 megawatts of power. We have a new modular facility that has about 6,000 square feet and 4.5 megawatts of power. But our main facility is shown down below. It has over about 50 megawatts of power itself, and each of those rooms are 24,000 square feet each. And they have some of the top computers in the world. We have older systems like Sequoia and Vulkan that run at 20 petaflops, take about 9.6 megawatts of power. But our newest system is called Sierra. It's getting dedicated this Friday, and it's going to be number 3 in the world, 72 petaflops and about 12 megawatts of power. These systems usually last about 5 years, and they get switched out. The maintenance contracts expire, so we are constantly in construction preparing for the next system that's coming about. So this shows basically our framework of how we meter our systems, our power, our mechanical systems. On the facility side, it's kind of hard to read, but we use our software to watch the electrical usage down to on the cluster and rack and node side. The system administrators look at the actual node temperatures, the thermal data that they can take in, and down at the CPU and core level, the actual users. So there's a lot of synergy that needs to be involved, but mainly on the node rack cluster and facility side, we're very interactive with our system administrators to look at the data, and it all goes back into this OSI soft database that we can look at our trends and analyze any electrical issues possibly, and analyze it through our BMS system. So once we get that data, what we do with it is, our biggest concern is to site next generation HP systems called ATS machines, advanced technology machines. We always have to know what we're using and be able to to show what kind of capacity that we have at our facilities. With these huge block loads, forecasting and talking to our utility company is important, so we could notify them of any power swings. And then we have to work with our users to optimize the system's efficiency. Our biggest goal is to turn as many of our megawatts into flops, floating operation points per second. And also look into possibly moving more into water-cooled solutions and cost savings. And then most recently, we're looking into troubleshooting and maintenance of our essential mechanical equipment, basically seeing if we could get away from time-based maintenance and go towards as-needed maintenance. So for these ATS machines that are coming, we have to do alternative analysis of what's coming up and know what we have, and we have to analyze if we have to build a new facility, if we have to remodel our existing, and compare all the costs for that. So one of the issues is that we're planning to evolve in planning guide. We are talking to vendors, and all we know is that possibly exascale computers coming in 2021, and it could be up to 40 megawatts. So we really have to work with those companies and know what we have, so we can sort of build to a moving specification. But once those computers come in, we run the systems, we look at its peak performance, its average performance, and then we're able to either consolidate some of our existing systems or, and most importantly, report back to the system manufacturers so they could plan for the next machine and also sort of hone in their own specification for that machine. One of our opportunities that we had was to consolidate some of our water-cooled solutions. Sequoia and Vulcan used to be on their own cooling loop, and we found that during normal operation that those two systems could actually be on one system. And so we installed some new piping, consolidated the systems, and we had a whole vacant cooling loop for the next ATS machine. So with these huge block loads, forecasting and reporting is important. Our utility company requested that whenever we have a 750 kilowatt swing over a 15-minute span, we report to them just so they could either make sure they have that amount of power available to supply to us, or if we're not using the power, to sell it back to the market. Over a 3-year span, we had about 1,400 alarms or alerts, and 8.4% of those were due to just the high-performance computer, either ramping up using certain runs or just powering down. So when exascale computing comes in about 2021, we're expecting huge swings of power. So that's something that we have to start getting into. And then also notifying the utility that we're doing maintenance on a system so they can plan for that power change. So one of the neat things we had the opportunity of doing is looking at a system that was just air-cooled and looking at it when we modify it to make it water-cooled. So this is the node temperatures for a system called CAB. It's 23 racks, about 100 kilowatts. And it shows basically, in the blue is the node that's closer to the inlet temperature, inlet fans, and then the red is a little farther into the rack. But you can see it's linear, and as the temperature rises at the node, more power is needed to do an average run. There's a few outliers that's due to probably manufacturer variabilities with the fans. But then once we made it water cooled, you can see in the green and the gray dots there, that shows that in all the temperatures homogeneous. We're getting constant temperatures to each node, and all of the power usage is consistent. So it made it a lot more efficient. So then, so the lower temperatures reduced the power leakage power, made the whole system more efficient. This is showing the efficiency of the computer. It's the instructions per cycle per watt. And this is before with the air-cooled the higher temperatures is less efficient with the